So in last lecture we completed the types of fluid. So in this lecture we will understand the surface tension. Okay. So suppose there is a fluid here, there is a fluid, okay, and outside that there is a gas, okay. There is a gas molecule outside that. This is the one gas molecule, another gas molecule, there is a other gas molecule, and here there is a liquid molecule are there, okay. So in between there are interface are there. So there is a liquid gas interface. So this is the interface are there. So in liquid region every molecule have attraction force. So this is known as cohesive force. When same molecules attracts each other, that is the cohesive force. So that's why the force are balanced here. But in this region there is a liquid molecule, here also liquid molecule, but here the gas molecule. So due to that there is liquid molecule, so here there is a liquid molecule, there is a gas molecule. So due to that there is a adhesive force. Adhesive force means dissimilar molecular attraction is there. So due to that surface tension is coming to the picture, okay. So adhesion force is there, so due to that surface tension are coming. So let's try to understand the definition of surface tension. So it is the apparent tension accepted at the interface of liquid gas, liquid. It is the property of the liquid. Very important. This is the property of the liquid. So in interview question they ask what is the definition of surface tension, what is the viscosity, okay. So try to understand that. So it is due to unbalanced cohesive forces of liquid. Surface tension is due to cohesion. As temperature increases the cohesive force decreases, so surface tension decreases. So here so with respect to temperature, surface tension is due to cohesion. As temperature increases, if the temperature increases then the cohesive force decreases, okay. And impurities, that means detergent, so impurities increase surface tension but detergent decrease the surface tension, but salt, that is NaCl, increase surface tension. Surface tension is the surface energy per unit area. So this is also very important. Surface tension is the surface energy per unit area, and surface tension is the normal force per unit length. We will understand in next. So surface tension is the normal force per unit length at a liquid surface, okay. So just remember this data. Surface tension of liquid air interface, that is water air interface, that is 0.072 Newton per meter. Surface tension of mercury air interface, that is 0.49 Newton per meter, and surface tension of mercury and H2O, that is equal to 0.42 Newton per meter. And what is cohesive force? Cohesive force means same molecules attraction, and adhesive force means dissimilar molecules attraction, okay. So consider, so this is a small area A1, and what is the energy? So E is the surface energy. So energy of that area, that is sigma into A1. Sigma is the surface tension. This sigma is the symbol of surface tension into A1. And suppose this is area A2, so E2. So what is the energy required to increase the area A1 to A2? So consider this is area A2. So what is the energy? E2, that is equal to sigma into A2. So surface tension, that is equal to, we know that sigma, that is surface energy per unit area. What is the unit? That is joule per meter square. So joule means Newton into meter by meter square. So meter and 1 meter cancel, so Newton per meter, okay. So sigma, you can say that is surface tension sigma, that is equal to F by L, because here the unit is Newton. What is that? This is a force unit and this is meter, means this is the distance unit. So F by L, surface energy, that is sigma into area. Okay, so what is the work done to create the area E2 minus A1? So that is equal to E2 minus E1, that is equal to sigma A2 minus sigma A1. Sigma is the surface tension, so W, that is equal to sigma into A2 minus A1. So sigma, that is equal to W by delta A. Okay, and here sigma, that is equal to Fs by L, that is the Newton meter. Okay, so try to remember this point here. For the given fluid, spherical geometry has minimum surface area. Due to that, minimum surface energy, that is more stable geometry. Okay, so liquid droplet and bubbles are naturally spherical. So this is very, very important. For the given volume, spherical geometry has minimum surface area, that is the minimum surface energy, that is more stable geometry. So the liquid droplet and bubbles are naturally spherical. So this may be any volume. So here this it may be shaped like this, it may be shaped like this, but it is always spherical because it's try to minimum the surface area. It's try to so spherical geometry has minimum surface area, so that's why droplets are always spherical. Okay, so this is the liquid droplet here. Okay, so this is the liquid droplet here. Okay, so for liquid droplet, E, that is equal to sigma into As. So sigma into what is the area of sphere, that is equal to 4 pi r square. So r is the radius of the sphere. Okay, for liquid droplet. So E is the surface energy. So Es, that is equal to sigma into As, that is equal to sigma into 4 pi r square. Okay, and for soap bubble, so here this is soap bubble. For soap bubble, there is air inside and there is air outside. So there is a thin layer in between. Consider the inner radius, so this radius, and outer radius, this radius. Consider this is same because this layer is very thin. So Es, that is equal to, we know that sigma into A, so sigma into 4 pi Ri square, because in that layer. So Ri is the inner radius, so sigma into 4 pi Ri square. So 4 pi r square is the area of the sphere, of the inside sphere, and outside sphere, that is 4 pi r0 square. So Es, that is equal to 2 sigma 4 pi r square. So this is for soap bubble. So here there is a small slope bubble and there is a large slope bubble. So for small slope bubble, what is E1, that is equal to 2 sigma 4 pi r1 square. We know that 2 sigma 4 pi r square. So for here there is a inside radius, that is equal to outside radius, that is equal to r1. So 2 sigma 4 pi r1 square, and here that is 2 sigma 4 pi r2 square. So what will be the work done? Work done, that is equal to E2 minus E1. So that is equal to 2 sigma 4 pi r2 square, this minus 2 sigma 4 pi r1 square, this. So that is equal to 8 pi sigma r2 square minus r1 square. This is very, very important. Now try to understand one question. This is also important. A spherical water drop of radius r splits up in air into n smaller drops of equal size. The work required in splitting up the drop, okay, you have to calculate the work done. Okay, so here in question that is given, that is volume of the large volume sphere, that is equal to small volume into n times into small volume. Okay, split into n smaller droplet. So consider the smaller droplet radius, that is smaller, and capital droplet radius, so larger droplet radius, that is capital R. So here the 4 by 3 pi r cube, that is equal to n into 4 by 3 pi r smaller cube. So from here you can get the relation between r and capital R. So from here you can calculate the work done, that is E2 minus E1. So E2, that is equal to n into sigma into 4 pi r square. So this is for smaller droplet, n multiplied by n minus sigma into 4 pi r square. So from here you can get how much work done is required to convert the spherical water droplet into n smaller drops. So this is my handwritten notes. You can download it from the description. The PDF link is available in the description. Thank you.